Hello, my name is Hir Patel, and today I'll be presenting my Physics 2212 Lab 3, which is on circuits. I'll go through the introduction, the purpose, important concepts, the observed model, the computational model, results, uncertainties, and finally move on to relevant questions. This experiment focused on understanding DC and RC circuit behavior from a macroscopic perspective. It explored physical principles such as charge conservation and energy conservation in electrical circuits. I constructed and simulated circuits with resistors and capacitors to observe current flow and voltage differences. I used both real multimeters and PHYS2212 simulators to verify theoretical predictions. I investigated the charging and discharging behaviors of capacitors in an RC circuit, and finally emphasized consistency with Kirchhoff's rules and exponential decay relationships in capacitive systems. The purpose was to predict current and voltage distribution in simple resistor networks using Kirchhoff's laws, construct series resistor circuits physically and simulate them virtually in PhET and compare these two models, use multimeters to measure current ammeter and potential difference voltmeter, replace meters in reserve connections to test current direction and circuit behavior, investigate RC time dependence by measuring voltage across capacitor over time, and finally compare measured values with theoretical predictions to validate the models. Some important concepts that are used are Ohm's law, which is V equals IR, which relates voltage, current, and resistance in ohmic devices, Kirchhoff's loop rule, which is the total potential difference around any closed loop, which equals zero, and Kirchhoff's junction rule states that current into any junction equals current out. Resistors in series always share the same current, and voltages across each resistor add to the battery total. Capacitors store electric charge and energy, and voltage across capacitor follows the rule V of T equals V of 0, e to the power of negative t over RC, when discharging an RC is a time constant where voltage drops to 37% of its original. And electric field is the slope of a voltage versus position graph, and it's steepest across resistors. In the observed model, I constructed a series circuit with two 1.5 voltage batteries with a total of 3.0 voltage, one 47 ohm resistor and one 100 ohm resistor, and two ammeters to measure current before and after each resistor. The simulation, the ammeter reading showed current I of 2 equals I of 1 equals 0.024A, and across the 47 voltage, we had a negative 47 ohm, a negative 0.96 voltage, and across 100 was negative 2.04, and the two batteries had a positive 3 voltage total, and the voltage graph showed a stepwise drop verifying energy conservation. When using the PhET model, we had similar values, with R of 47 having a 48 value and R of 100 having a 102 value, and the wires and ammeter assumed 0, and the predictions matched experimental data to agree that showed that both experiments were done accurately, with 47 being approximately 48 and 101 being approximately 102 in the purpose of this experiment. And we demonstrated Ohm's law in a simulated circuit. Using the PhET circuit construction kit, I simulated RC circuits to visualize charging and discharging behaviors in real time. The setup included a 9V battery, a 0.2 F capacitor, and light bulbs of different resistances, 10 ohm and 20 ohm. The brightness of the bulb served as a visual indicator of current strength. As the capacitor charged, the bulb dimmed, illustrating the exponential decay of current. Timing each phase with a stopwatch allows us to compute the time constant tau and compare predictions and observed values. Some uncertainties of this lab, like any lab, were that the ammeter readings may vary due to skill selection. The human stopwatch timing introduces delay of about 0.1 to 0.5 seconds, depending on reflexes. Rounding in voltage readings affects calculated resistances, assumes ideal wires and components, and zero resistance in wires, which may not always be true, and simulation fidelity may slightly differ from physical hardware. Some relevant questions now that I'll go through is, if the experiment were conducted in real life with an actual ammeter instead of an ideal simulated one, the results might differ slightly due to an internal resistance of a real ammeter. While ideal ammeters have zero resistance and do not affect circuit behavior, real ammeters typically have a small but non-zero internal resistance, often in the range of a few ohms. This internal resistance would slightly reduce the total current in the circuit by increasing the overall resistance. Depending on how the ammeter is connected, this could also impact the voltage drops across each element, especially in sensitive or low resistance setups. The altered current might slightly change the readings of other components and could skew measurements if not accounted for. Furthermore, connecting a real ammeter improperly, e.g. in parallel, could damage the device or alter the experiment entirely. Care must also be taken to ensure the current flows into the positive terminal to yield meaningful positive readings. Overall, real-world measurements are subject to additional precision and calibration limitations, making simulations idealized but not entirely representative of physical conditions. Secondly, in a real-life scenario where the real battery charges a real capacitor with no resistor present, the prediction from the ideal model would be that the capacitor charges almost instantaneously. According to the equation, tau equals RC if R equals 0 and tau equals 0, implying infinite current and 0 time to charge. However, in internal resistance wires or contact points, attempting to charge a capacitor with essentially zero resistance would create a surge of current limited only by these parasitic resistances. potentially damaging components or causing overheating. Additionally, a real capacitor may not be able to handle the initial current spike safely, risking breakdown or explosion. This highlights the difference between idealized theoretical models and the limitations imposed by physical systems. Real batteries do not act the same way as in the PhET model, and the actual behavior would be rapid but not instant, charging process governed by real-world constraints. This deviation underlines the importance of including real resistance in practical circuit designs and shows that this lab, while shows how this would work in real life to an extent, is not completely accurate. Thank you for watching.